Good morning, class. This is Mr. Burke, and we're going to go through Network Fundamentals Part 2. This is part of the Module 2 network component in class Info 393. Let's get started. All right, quick look at the agenda. In Part 1, we covered the architectures, the topology. We talked about network segregation, segmentation, and isolations, things that are done to secure the network, make the network more secure. We also talked about some security devices and very specifically where those devices are placed to add security to your network. And then we talked about security zones, things like DMZs, which are buffer zones, to limit activity from getting into external activity, prevent it from getting into your internal network. We talked about the internet, the intranet, the extranet, and wireless zones. So I encourage you to go back, look at that presentation, and review that recording if you have questions about those topics. Today, we're going to get into more the logical definitions of a network. We're going to talk about protocols, network protocols, and very specifically, we're going to go deep into the internet protocols. We'll also talk about addressing, and we'll focus in on internet protocol addressings, version 4, version 6. We'll talk about MAC addresses. We'll talk a little bit about Wi-Fi addresses, ports, and things like that. But the key is to expose you to those concepts, the addressing concepts that are used to route data from a source to a destination. In our next class, we'll get into the packet delivery, essentially putting this all together and how data starts from a source, a user's workstation or application, and routes through the various layers of protocols on its way physically through the network and to its destination, and ultimately to an application, an end user, or a recipient at the target destination. Let's keep going. Always feel it's important to have context in terms of what we're looking at. So over to the right, you see an example of a university, a very high level conceptual example of a university network with wireless LANs in the office. And LANs are local area networks, and those are clusters of workstations that have been connected into the internal network. Typically, they're wired in. We also have the dormitories they may have and or labs in the campus that may have workstations directly connected into the network. I think we'll focus in on the wireless because more and more our predominant user base is coming in through some kind of wireless connectivity into the university network. The key thing on this chart is the firewall. The firewall is what defines what is an internal network, in this case, a university network, from the rest of the external public networks. If we go beyond the firewalls, which is filtering, blocking, and controlling what gets in and what gets out, if we go beyond the firewalls, you see the external networks, things like the internet. One thing I did want to point out on this chart is we have internet service providers. The internet may be free to use for you, but it is not free. So all kinds of people who have subscriptions and pay for services or have mobile service and things like that, they're actually paying for all the connectivity into the internet. So a quick definition of the internet, it's simply a huge network of connected devices that use standards that allow for free and open interchange and exchange of data. So these are devices. Doesn't mean you have a web page, although web pages are a huge part of the internet, but it can be any device that is connecting with other devices using the internet standards. Your printer could be on the internet, your security camera, your doorbell, your thermostat, your car, all of those devices could be on the internet. It's not just web pages. Okay, over to the left side of this chart are the concepts that we really want to call out as we go through these fundamental presentations. protocols and what they are. We're going to talk about that today. The different types of networks, local and wide area. We talked about that in the last class. I encourage you to go back and look at that some more, but that's essentially how you can lay out, be it in your local geography, your local site, how you can network together, or if your team, organization, coworkers, colleagues are elsewhere, you can use wide area networks to essentially define a network regardless of geographic location. Wireless, we'll talk a little more today, but that was in the last presentation of how wireless is set up. We didn't go deep into all the technologies, but simply how do users connect to wireless and how are those wireless access points laid out in your building, facility, dormitory, Starbucks, whatever. Switches, hubs, bridges, and routers, those are the devices, if you will, behind the walls, in the closets, in the basements, that is actually routing the data to and from its source to its destination. We'll talk a little more today, a little more about that as we talk about the protocols. Then we have some concepts we're going to go into more today. Subnetting, how you divide a network up. Firewalls, we talked about that a minute ago. DMZs, a DMZ is simply a buffer zone. I think that's in Tuesday's presentation. And proxies also. A proxy is a dummy server, an intermediary. So you do not send data directly from your device into the internet. You send your data to a proxy server that sends it on its way. And then data coming back goes to the proxy server before it gets to you. It's a way to have a device which is a buffer between your device and the public networks. Datagrams are simply data. We have a chart in this package on datagrams, but it's how we define the data that is flowing through the network. Then we have a series of addresses that we'll go into today. DNS, which is your domain name service. It's like your yahoo.com, your google.com, your amazon.com. That is a textual, human readable, human friendly name for your address. You don't have to have a domain name to participate in the internet, as long as you have an IP or an internet protocol address, 9.3.6. Whatever, then you can participate. Any device that has an IP address, the numeric address, can participate. Ports, we'll talk about that a little more later, but that, in addition to your IP address, determines exactly what application on the server or device you're communicating with, you're trying to actually connect with. And then finally, the MAC address. The MAC address is the physical address that is assigned by the vendor to each device. So a printer has a MAC address. Your laptop has one. Your phone has one. These are manufacturer provided identifications. It's like a serial number. We'll talk about that a bit on the internet. And then finally, the key concept we want to talk about is, as we go through network fundamentals, we're using a security lens. We're looking at the security perspective of the network. We could talk about performance. We could talk about availability. We could talk about function. Instead, we're really going to focus in terms of how is security affected, impacted as we lay these network capabilities and devices in place. Okay. So we're into part 2. We're into network protocols. This is high level what we're going to go through. So I'll start in each by going to each presentation or each page. First of all, some key concepts, and these are address concepts. The IP domain name, we talked about that a minute ago. That's simply put your Coca-Cola.com, your Yahoo.com, your Amazon.com. You'll see over to the right an example that has a www. That's great. That's been used quite a bit. The www isn't not needed. You can put in dreamhost.com and your browser will resolve that and find dreamhost.com as long as it has been assigned to some underlying IP address. The IP address is the numeric representation of the address. Normally it is 32 bits long, that's IPv4, both those addresses are depleting and depleting rapidly. So now IPv6 has been introduced, which is a longer address space, 128 characters. Okay, the IP address is what you need to participate in the network. It is a logical assignment. It is not permanently assigned to you. So when you connect via wireless, you are temporarily given an IP address. It may be a private one. We'll talk about that later. The port is the logical endpoint. In addition to the IP address, the port will determine exactly what application you're talking to. Wi-Fi, there are certain IDs that are used when you connect to a Wi-Fi device. This is before you get to the internet. As you are talking to the Wi-Fi access point, SSIDs are used. The SSIDs define the network you're connecting to. Maybe it's called Starbucks, it's called business school, it's called dormitory one. ESSID is the same thing. It is the network the label, the name of the network you're connecting to. And the BSSID is the MAC address of the access point. And then finally, let's get to MAC address. That's that physical address that is assigned by the manufacturer to your device. And ultimately, as data flows through all these logical layers, it has to get to a physical layer, and bits and bytes, zeros and ones are being sent to some device, a printer, a scanner, a fax machine, a laptop, and all of those have MAC address. So we have protocols next. And these are agreed upon formats for data exchange. We'll talk about the frameworks that are used. There's either a 7-layer or a 4-layer framework we'll use. Most networks in terms of protocols use Ethernet or the Internet Protocol. Ethernet is at the very lowest level. That's where you are connecting your device into the network. In addition to Ethernet, you might be using Wi-Fi. So Ethernet and Wi-Fi are the ways the devices initially connect at the lowest physical level. Then we have the internet protocols. That's more at the logical level, but that's how your data, your connection gets to its target. It's the routing, it's the connecting, the addressing that goes on in the middle. We'll talk about that in a minute, but over to the right, you'll see two of the key internet protocols being TCP and UDP. Data can be encapsulated. That's on a separate chart. Let's get to that separately. There are different models that are in place for protocols. OSI is an open system interconnection model, 7 layers. TCP aligns directly to the OSI model, but it has 4 layers. So you can see the example over to the right. I'm going to go into that in more detail. You don't have to memorize everything, but on a couple of these, I just want you to know are the key layers. Okay, so OSI is a 7-layer, starts at the top with the application layer. That's what services the user. And it goes all the way down to the physical layer. And that's where the bits and bytes are moving back and forth between devices. So you read this from top down. And then when the data gets to its location, you read it bottoms up. I have an example of that later in the presentation. The data that flows, let's go back, just talk about it. I'm going to walk down through each layer and just kind of quickly give you an idea of what each layer is doing. At the top, the application layer is servicing the user. Those are the protocols and applications users use to access web pages, to do email, to do word processing. Whatever you're doing on the computer, the protocol that's managing that is being used at the application level. The presentation level will take the data from the application and may start compressing it, synchronizing it, and encrypting. So I think the key thing we're interested in is encryption can be applied at the presentation level. Session level establishes a dialogue with an end user, but it's not connected yet. It kind of sets up the rules for who you're going to talk to. And it may include some some control information that's needed for emails that's going to another location, or for some data streaming content that's going to a user. The transport layer and the network layer, that's where some of the heavy lifting gets done. The transport layer is where you put a protocol in place to say, hey, do I want to guarantee my data gets to its location, and essentially confirm I have a connection, I'm sending the data, they receive the data, they got it all, and it's error-free? Or do I want to use a faster protocol that gets the data to its end location faster, but doesn't necessarily have all the controls and return receipt information? The network layer, that's kind of where the heavy blocking and tackling goes. That's where the protocols will determine how the data gets from point A to point B. What's the best, fastest, most efficient route? And that's where routers come into place. They're using IP addresses to figure out where they're going and how to get there, and so on. So IP addresses at the network layer. At the data link level, uh, that's where that data starts to get translated down into bits and bytes that the device is going to use. So the data, we'll talk about it a little later, is put into frames, and we start a conversion from IP addresses to physical addresses based on getting to its physical end location. And then the physical connection, that's actually when you connect with a device and you send bits and bytes, zeros and ones, the data in zeros and ones, raw format, to that device. Okay. The data itself, and I think this is what I would call out. The data itself comes in a number of different formats. First of all, in an internet protocol environment, we use a packaged switched network where the data is put into chunks, and those chunks then are routed on their way. The chunks may be separated and routed in any order as long as they get to their destination, and then it's sorted out at the destination to put them back in the correct sequence. So a datagram is basically what terminology do we use for the data at the various levels, at the various protocol levels. I'm going to call out the formats on this chart. For example, at the application presentation and session level, we're using data. It's called data. And that's kind of self-evident. And you're up in your host, and that data hasn't really left yet. It's getting prepared to leave. Once the data is kind of getting ready to hit the wires, if you will, get sent to its destination, it is placed into segments, and there's additional addressing information added, including the ports. What port, when we get to our destination, exactly what port or what application or what protocol do we need to talk to? Then the segments are put into packages and further subdivided, and the packets are all about routing. It's all about routing, and they'll take big chunks of data and break it into smaller chunks of data and put IP address destination and IP address source headers on it, so you know who it came from and where it's going. The packets then are broken down further into frames, and the frames are where you take those packets of data and you put a MAC address, the physical address of the device you're going to. Up until now, it's all been logical. You've had temporary IDs that have to be translated into these physical IDs, and that's where the frame comes into place. That's where that process starts. And then finally, the frame will break the data down and deliver the data in bits. And that's at the physical layer. And that's the zeros and ones that are actually transmitted across the media to the physical device. Okay. We kind of talked about encapsulation on the last chart, but simply put, that's where we move from layer to layer. And the example here, or the analogy would be, it's like putting a letter in an envelope, putting that envelope in a bigger envelope, putting that envelope in a bigger envelope, and so on. So everybody who gets their package or their copy of the layer, all they look at is on the addressing on the outside label. They don't need to open it up and look at the data within. So this is a way to add security through encapsulation. The data within can be encrypted. All they need at the packet level, segment level, and frame level is where's this coming from and where's it going? So that's encapsulation. It's a way to add security by keeping each layer or each protocol at their respective layer only focused on the addressing. I think we've covered these items, but I am highlighting in yellow the key datagrams. At the level 4, the transport level, we're working with segments. At level 3, the network level, where we're doing routing, we're working with packets and IP addresses. At level 2, at the data link level, we're working with frames and MAC addresses. And at the level 1, the physical level, it's raw data or bits, data bits. So this diagram just kind of helps see the flow. We start at the upper left at the application level. That's where the user using some application or some protocol at their level is doing some function and ready to transmit data or request data. And that goes from top down, layer by layer by layer, into the transport layer, where again, it becomes a segment. It goes to the network layer, where that request becomes a packet. It goes to the data link level, where that request becomes a frame. To finally, it becomes the bits and bytes at the physical layer that it's going across the media, going across the transfer media. When it gets to its destination, it goes up the layers. So bits and bytes get reassembled back into frames, gets reassembled back into packets, gets reassembled back into segments, and finally into data. So you're unpacking the data, the encapsulation, you're de-encapsulating, if that's a term, as it gets back to the application, and it becomes some readable data that the application on the other end, be it a web server, an email application, whatever, can consume and present. Okay. We talked about packets quickly, but in the internet protocol environment, we do use packetized networks where data is broken into smaller chunks. The protocol determines the size of the chunks based on various factors. The intent is to manage it more efficiently and get it to its end destination as quickly and safely as possible. One of the issues with packetizing is you could have fragments, packet fragments that kind of get lost, I won't say stolen, but mishandled. But the data turns into fragments, and it's a challenge to reassemble it back on the other end. That's why many times you'll use a specific protocol, TCP, which guarantees the connection and it guarantees the delivery of all the data. Otherwise, it stops the process. Now we're going to deep dive into the internet protocols. So we've been talking about protocols in a very general term. Now we're going to really focus in on the protocol or protocol suite that is used in the internet. I have listed over here the key ones that we'll talk about. TCP, which is connection-based protocol, guarantees that your connection is established and your data gets to its location and it is complete. UDP is a faster protocol, also an internet protocol. Its challenge or objective is to get your data to its end location. It's best effort and get it there fast. It's not going to guarantee it's going to get there, or it's not going to guarantee that it's all going to get there. And there's specific applications where that's fine. Data streaming, music streaming, various things where if you have a little blip, you probably won't even notice it. But the key objective and challenge is to keep the data moving and moving fast, not to slow things down with a lot of error recovery and error checking type activity. There are some other protocols at the network level. For example, you have ICMP, that's network messaging. That is not user messaging, but some things we do in the network to check status. Is a network device up and running? What's the response time of the network device? So those are some kind of system messaging activities, and they run on a protocol called ICMP. And then ARP, that's the protocol that's used to translate internet protocol addresses back to MAC addresses, And then finally, TCP, as we talked about up top, that's the one that guarantees the connection. There's actually what's called a three-way handshake. We'll talk about that in a minute. But that's what occurs to ensure, to acknowledge and confirm that a connection is established before we send the data. Okay. Want to call something out in the Internet Protocol. Again, the Internet Protocol is a suite of protocols, and I highlighted on the prior chart some of the key ones. In addition, there's addressing schemes that are going on, which are IPv4, IPv6. We're going to talk about that in a minute. IPv4 is the predominant used IP address scheme. That's the 9.3.6.7 type address. The challenge there is that's 32 bits long and we are running out of addresses. So IPv6 has been introduced. It's simpler, it's faster, it's a longer address. It's 128 bits long. So it's not as human friendly. It's almost impossible to remember, but it's extremely efficient within a computer system. The challenge is everybody's still using IPv4, so transitioning to IPv6 is the challenge, but eventually that will take over as the predominant addressing scheme. An IP packet. We talked about datagrams. A packet is basically a unit of data that's moving through the network. And the key thing we call out here is all packets will have a header and it'll have its data or the payload. And the header is what the protocol is really working with. It'll have the where's it going, where's it coming from, and any other control information that you need to be aware of, or that protocol needs to be aware of. And TCP and UDP, that's a connection-based protocol versus a connectionless protocol. We'll talk about that more in a second. We'll talk about it now. At level 4, when you do transport level, a decision has to be made as to what protocol are you using. Do you want to guarantee the connection and guarantee delivery? And in that case, you're going to do a three-way handshake. Or do you want to run it as fast as possible? And that's UDP, User Datagram Protocol. And that is connectionless, but it usually is pretty good and it runs much faster. That tends to be used when you're doing data streaming. So this is a decision that's made when you're transmitting data by selecting one of these two protocols in the internet. If you select TCP, which is, again, this is when and how you determine, you guarantee that there is a connection and that the data does arrive. The first thing that happens is a three-way handshake. Starts with a synchronized request, goes from the requester, your workstation, to the server. A synchronized acknowledgement comes back from the server saying, hey, yeah, I'm ready to connect. And then you acknowledge back to that server, okay, agreed, we're connecting. So you have this three-way exchange and a connection is established, and then the data starts flowing. After everything's done, an RST message comes across, and RST basically ends the session. So I think the key takeaway here is before data is exchanged on TCP, a connection is confirmed and established. IP addressing. I think this is the last section of this presentation, I think, or just about, but we'll talk quickly about the domain name and IPv4, IPv6, subnetting, and submask. And then we'll talk quickly about network address translation. As mentioned on a prior chart, the IP domain name is something, it's a human-friendly, readable, Coca-Cola.com, Yahoo.com. Those organizations essentially buy the rights to own that or reserve the rights, and they pay for that to own that. And then that is a way to communicate with their at least main web page and their email domains. Okay, you don't need a domain name to participate in the internet. If you have an IP address, you can participate, and an IP address is the numeric representation of that IP domain. Subnetting. So IP addressing, major organizations can reserve a, if you will, range of IP addresses, and they do that through their internet service providers. Um, and again, they pay for that if they reserve a range of IP addresses. Subnetting allows them to take that range and then subdivide it up into specific networks. Maybe part of the range they want to use for the dormitories, part of the range they want to use for the administrative offices, part of the range they may want to use for guests. But subnetting essentially takes your IP address ranges and you subdivide it into smaller networks. It improves your ability to control, monitor, and secure those subnets. Finally, on this chart, something called Dynamic Host Configuration Protocol, DHCP. That's what happens when you come in and you open your laptop and it connects to a Wi-Fi port. At that point in time, an internet protocol, an IP address is getting assigned to you. And behind the scenes quickly they discover you. There's an offer from the access point to say, I'm going to offer you an address. You come back and say, yes, I want an address, and they acknowledge, and they'll assign temporarily an IP address for that session. When you shut down and you go somewhere else in the building or to another building, you'll go through this process again and you'll be assigned a different address. So your address can change dynamically as you connect, exit, and then reconnect somewhere else or at a later time. All right. I'm going to just pause here. This chart should kind of jump out at you. This is the addressing scheme for IPv4 versus IPv6. The takeaway here is IPv4 is 32 bits long. So that limits the number of different unique IP addresses to, I think, to like 4.5 billion. With the growth of the internet and data around the world, we're depleting that rapidly and running out of addresses. So IPv6 has 128 bits of addressing data available, and it almost gives us an infinite number of addressing options. It also has enhanced security, and it's designed to be more efficient and all those good things. The challenge is getting people to transition from V4, which they're used to V6. I will mention over to the right, in both of those scenarios in your address, IPv4, part of your address identifies the network you're in, and part of your address identifies your host or your device or the server you're talking to. So depending upon the address you're using, the class of the address will dictate how much of the address is used for identifying the network or the network ID versus identifying the host or the host ID. You'll see in IPv6, they basically break it down half and half. 64 bits of the 128 bits identifies the network, and 64 bits of the 128 bits identifies the host. Okay. And this will jump out as we talk about subnetting. So subnetting is the network ID. So you can use multiple network IDs within your greater a range of addresses for improved management, control, and security. We can jump over this chart. We've hit all the key items. The key takeaways: IPv4, 32 bits long. We're running out of them, but it's widely used. IPv6 has a longer address space, 128. It's much more expansive. It's more secure, and it's more efficient. It's faster. But it's hard to get people to adopt or transition to it. Subnetting, we called that out earlier, but if you have a range of IP addresses, you can divide your range up amongst subnets. And it's basically by defining in your addressing that certain range of IDs are in a certain network versus other ranges are in other networks. The subnet mask basically says where in the address do we identify the network? Is it the first byte or the first 8 bits? Is it else? Now, don't get hung up on this, the subnet mask. I'm going to point specifically to what I want you to look at on the next chart. But essentially a subnet mask that says, where is the network address? The subnet mask is the network address. If you're looking at the entire IP address, what portion of that is my network? Okay. I'm going to jump over 2 charts as we talk about how do we identify the network in a subnet. There's something called classless interdomain routing, blah, that's a mouthful, also known as CIDR. And if you see an IP address with a slash and a number, and if you look at this chart, look at the yellow highlighting, you have 192.168.1.168/24. The subnet is the /24. And what that means is 24 bits of this address is describing the subnet. What I'll ask you, as you get more advanced in networking, you'll learn how to work with that a little bit more. But for right now, when you see that /24, you know, oh, there is a subnet going on. And this is an example of a CIDR type address. And that 24 bits, in this case, are being used to identify the address of the network portion of my IP address. So it doesn't always have to be a /24. It could be a /16. It could be a /8. There could be various numbers behind the slash, but it tells you how many bits have been reserved for the network ID. IP addresses, there are different classes. Don't want you to get lost in this yet. Eventually, you'll learn more about it, but some of the IP addresses in the IP address range are reserved for private. They will never be exposed to the external network. They're for your device, it's private, it's internal, it never goes to the internet. Excuse me. In Class A, if you ever see a 10 dot something address, 10 dot something, 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 that is all private address ranges. It's to be used when you're doing things on your workstation that are only visible to your workstation or in a private internal network. It never goes out to the internet. Those are private addresses. There are also some addresses reserved at Class B and Class C. Don't want to go deep into that other than you can look those up. And I'm going to drop to the bottom right in the green box. You'll see something called loopback. That's 127. Any address that starts with a 127. Loopback is where you're doing some activity on your device and you want to display the results to your device. So it's like you're simulating a network, but you're displaying the results back to your own workstation. And you may see that, oh, that activity has been assigned to 127.0.0.1. Okay, but just be familiar what loopback is and 127. In the study guide for the quiz, I'll highlight kind of where I think you want to be. You don't have to remember all of these. I will ask for Class A. If you see a 10 dot something something, that one should be easy. That's always a private address. And a private address is never exposed to the internet. And finally, and I know this has been a lot, but finally we have a network address translation. And that is a translation device tool process that's part of your network as you talk from your private network to the external world, to the external network. The network address translation will convert or translate your private IP address, which is non-routable, to a public IP address that can talk to the internet, which is routable. So we may have everybody at the Howard, in Howard is assigned when they log in the morning, a private IP address internal to Howard only. And only when and only if a user tries to go to the internet, they then go to the network address translation tool, and it will assign temporarily a public IP for you to communicate from your IP to a public IP to the internet. Response will come back, and that network address translation facility will know from that public IP, oh, that's this private. It keeps track of your private IPs that are talking to public IPs. This is a great way to ration the public IPs that an organization needs. You can have one-to-many. So you could have one public IP and everybody internally shares that dynamically. Only when you need it do you get to use it. And when the response comes back, the NAT will translate the response from that public IP back to your specific private IP. Okay. So here, just know it's a translation tool from private to a public and public back to private, and it's one-to-many, that you could have many private IPs using the same public IP via the network address translation. And that's it for part 3. I know that's been a lot. I'm going to get the study notes out over the weekend for the quiz, which will really focus in on the kinds of things we would ask in a quiz or exam. With that, contact me if you have any questions. Feel free to text or email me, and I look forward to seeing you in the next video or class. Bye-bye.